Can you please think? Good morning, everybody. So we'll be starting our microprocessor stream very soon. Before we begin, so I want to tell you about the structure. So um, I've looked through the questions and they look they're fine questions. They're not too difficult to handle, intended to trick you. Anything. So before we begin, we'll go through a couple of formulas, a couple of facts that I think that if you knew that before, like beginning any other question, it's very, very simple. So these facts will cover everything from memory decoding to the memory formula, like the width and the address, to the file allocation table size formula. So the hope is that if you by the end of me going through the formulas, you would have gotten a grasp of everything, so that like probably maybe 60% of the questions will be very simple, just based on the formulas alone. And then the rest of the questions are just understanding and reading questions. You need to understand whatever that the question is asking of you, and then you can give an answer. Most of the questions too do not have a single answer. It's a choice that you have to make between this or, and that's how that's the way the questions are structured, right? So it all depends on you and your understanding. So I will try to explain it as much as possible. Hopefully you would get. And also the assembly language part of the questions. I don't know how I would tackle that. I don't know whether we'd give out resources to learn it, just to give answers just like that without explaining it. It's something that I'm thinking about. If you could, if you have an idea on how to go on with that too, you could help us with. As I said, we'll be starting very, very soon. So please be on standby whilst we get other people to join the stream. So if you have any friends that you think would benefit from this, it is 8:30, so they are still sleeping. Please wake them up to come and join the stream, because as the video will be up, the video will be uploaded for your own time to watch. But it is better if you are here and then you can ask questions to clarify everything. That will make everything a lot more. Because if you go and sit down and then the questions are slightly changed values, how do you get it right? So if you have any question, also please don't. But we are not shy of questions, right? Feel free to ask any question. So I'm your tutor for today, Paapa Kwesi Quansah. I'm in Electrical 3, and I hope we'd have a wonderful time. Yes, so please, since enough time has passed, so we can get to there. formula part. So before we actually begin solving the questions, you can in all that time you can call someone, you can call your roommates to come and sit by you. Or all those are, as I said, we're not shy of anything, so feel free. Okay. So right. As I said, we'll be starting with the formulas. The first formula that I would want to start with is the storage formula. S is equal to A times W. The writing is very, very bad. Please hold on while I move to print application so that would help with it. All right. So the first formula would be the storage formula. So there's a particular formula, S is equal to A times W. So if you have any problems, I feel like I should please let me know by typing it in the chat. There's a team here that is waiting to answer your questions. S is equal to AW. So if you have a system, storage system, right, and the storage system is described as having 64 kilobytes, a space of storage of 64 kilobytes. What that means is that there's some addresses and there's a width. So what this means is that you see your memory, a very, very high level overview of a memory will be like a matrix. So for each location, there's a particular amount of memory that it can store, right? And then like simply you can tell that if I want the storage of this entire thing, what I would do would be to multiply the number of individual locations by how much is stored in each location. You understand? With the number of addressable locations times the weight of the data, right? So if I give you let's say 64 locations, 64 key locations, I tell you that I'm storing 1 byte in each location, that means that your entire memory space of that particular storage will be 64 kilobytes. I hope this is understandable enough, right? And also, if given a certain number of lines, so this question has been popping up was the past questions, right? It goes like a microprocessor has 13 lines, so 13, 12, 11 lines, right? How many addressable locations are there? So in this case, giving the number of lines of the microprocessor, I want you to find how you would do this is the simple 2 raised to the power x, where x is the number of lines of the processor, so 2 raised to the power 13, and that would give you 8 kilobytes. Very, very simple. Hope you would understand this. So first formula. The second formula is FAT formula. So I've asked around and okay, so they didn't really teach us, right? They didn't really teach us. I don't know about other courses. I asked a telecom, I asked a biomedical student, and then they've also taught them. So I think that this will be new to everyone. So let's go. Right. So the thing is that in real life, your actual usable capacity of any hard drive, of any storage unit you have, right, is always 10x over some 2y. What this means is that the manufacturers will always represent your storage locations. For example, your hard disk will be presented as 1 TB, 1 TB. Your hard disk will be presented at 1 TB. Your pen drives are 16 gigabytes. They're not actually the same with how you think of memory, right? So um we define a particular formula. This formula doesn't have a name, it's just an easy way of helping us to find out whatever you're looking for, right? So in real life, so let's take a real life example so that it will help you think about it. So 1 TB would be represented as, so 1 TB is what the manufacturer will tell you. So what Seagate will tell you is the size of your hard drive. But you know this is not true. When you open your hard drive, it's normally 331 gigabytes. So where is the disparity coming from, right? So there's that. We define this as a particular ratio. I don't know what name you would want to give to it. Maybe the Agri ratio, something like that. Any ratio. So ratio times your the manufacturer what the manufacturer will tell you what the manufacturer will tell you minus so this is a very, very, it depends on what is happening, right? This that's why I'm putting it as plus or minus. It depends on what is happening. So when your ratio is defined as m over s, that is when you use a negative. If your ratio is defined as s over m, we'll use a positive. We'll get to what this means later, but please just keep this in mind. You would understand it all as time goes on, right? And plus or minus some f, where f is your FAT size. FAT stands for file allocation table size. So let's say that I want to find the actual usable capacity, actual usable capacity of my hard drive. What I'll do is to define some ratio. So now let's get to what these ratios mean, right? If your manufacturer, what the manufacturer will tell you is less than your actual usable capacity, you use this. So what this means is that the manufacturer will tell you it is 1 TB, but in actuality it is 931 gigabytes. So we use this formula. But in other cases, and this is how the questions normally are in the past questions we'll be solving. Normally it is the usable capacity. The usable capacity is always greater than your manufacturer's, right? That's how it's defined. So we'll get to a question. We'll get to a question soon. In fact, let me show a question so that you would know how this is. Uh, okay, teams questions are not here. So let me get to show some questions that's involved that. Okay, so perfect. 2015's first question. How this is that it tells you that it is discovered that the marketed storage capacity of the disk drive is always less than the actual usable capacity when the drive is formatted. So we're looking at that. It's discovered that the marketed storage capacity of the disk drive. So the marketed storage capacity is less than the actual usable capacity. So what this means is that the manufacturer will tell you that, oh, it's 10 gigabytes. When you go home and then you put it into your system, you realize that it is 13 gigabytes. This will never happen with our current manufacturers, but it's a good way to think about the question. You understand? So now let's get back to deriving our formula. Let's get back to deriving our formula. So if your manufacturer is your manufacturer size is greater than your actual usable capacity, use this formula, use this ratio, this formula for your ratio. Now, when your manufacturer size is less than your actual usable capacity, this formula is used. You understand? So now let's get to our terabyte ratio. We'll use our M over S ratio. So I just heard that the screen really wasn't showing. Um, um, okay, sure. Like, yes, please, it is been showing. Yes, it is showing. So we can continue and continue. So the rest of the team just arrived from slumber. So let's go through the first formula again. Sorry for all those who were here from the beginning. Please seek your Ventamaklu to argue. So please let's begin again. Okay, sure. So as I said, the intention was to provide a basis by which you could solve all your formulas very easily, solve all the questions very easily. Understand? To solve all your formulas very easily, solve all your questions very easily. You don't solve formulas. The first formula that we talked about was that um first one was S is equal to A times W, where the storage you want is equal to your addressable space times your width. And as I said, memory is thought of as a matrix, right? It's a good way to think about memory location. So if you're doing your project that you can incorporate this into it to help you better understand whatever storage system you might be using, whether your register file or whether RAM. So that's how it is. You have a certain number of addressable locations, 9 in this case, right? And you store some amount of memory in each place. You understand, in each location. So your storage here will be the number of addressable locations, which is 9 times the amount of memory, the amount of space each location can hold. So if we say that it is 1 byte, it can hold 1 byte, then your entire memory location is 9 bytes. So this is a 9 byte memory. And also one thing I didn't mention, if your each the amount of memory in each location or the amount of storage in each location is 1 byte, right? It is called byte addressable. So this is a byte addressable memory. If it is anything else, it is not byte addressable. So if I store, let's say, a word here, a double word, a quad word, I store a nibble, I store 1 bit. They are all not byte addressable. You understand? So this was the first formula that we defined. The second formula we wanted to define was your FAT formula, the file allocation table formula. And as I mentioned that they didn't teach us, right? We've not been taught this, but it occurs a certain number of times in the past questions, and I wanted us to go through it so that we can understand it, right? Perfect. In real life, the actual usable capacity, right? So in real life, the actual usable capacity would be represented as 10 raised to the power x all over 2 raised to the power y, something like this, right? So what this means is that your manufacturer will tell you some value, you go and put it into your operating system, and then it is not the same thing. It occurs quite often. You buy a 1 terabyte. So the 1 terabyte disc that I have, right? If it is 1 terabyte, they tell you it's 1 terabyte, but in actuality, you are using 931 gigabytes. That's how much it will show. So what accounts for this difference? What's the cause of this disparity, right? I'm sure we all want to know. So this is what happens, right? The actual usable capacity. So there's a particular formula that it helps to think about in this way. The formula will be that your actual usable capacity equals some certain ratio, right? And as I said, there's no name for this ratio, at least not to my knowledge. So you can use it, maybe the name of your boy, you can use it as that name ratio, right? So Agri ratio, that the quota macro ratio, right? Then you define this ratio, and then you multiply it by what the manufacturer tells you, right? What the manufacturer tells you, and then you add or subtract. Yeah, the additional subtraction is based on how you would define this ratio, right? You multiply by the manufacturers and add and subtract your FAT size. So as I said, let's use an actual real life example so that it will help to think about it. So the manufacturer tells you that your hard disk is 1 TB, tells you that hard disk is 1 TB. And then your FAT size. So FAT is not fixed, right? Your file allocation table size is not fixed. But for this particular situation, we'll assume it is fixed with an FAT of 22 gigabytes. So please, like, trust me that this is true, right? So this will usually be given in the question, or you'll be asked to find this. So this is usually the basis of your calculation. So trust me that this is true. Excellent. So as I said, when your when your ratio is defined as M over S, manufacturer over actual usable capacity, right? So when your ratio is defined as M over S, right? What you do is to define your class as your this your expression as a negative. What is it? You can take a screenshot if you want to, or write it down. I advise you write it down. And if you decide that it is S over M, it becomes plus, it becomes positive. You understand? So back to our real life example. You have some M over S. The M over S means that the manufacturer size is always greater than your physical, like what you put in your operating system and then you get. And this means that your usable is always greater than your manufacturer. And I give an example that when you buy a 1 TB disk, right, your storage is 931. So the manufacturer tells you 1 TB, but when you're using it, you can only store 931 gigabytes of content on it. And then I gave an example that in the questions, it is flipped rather, right? So this is 2015's past question. We'll get to it. The question says that it is discovered that the marketed storage capacity of disk drives is always less than the actual usable capacity, right? So this means that S is always greater than M. So we use our second formula, right? We use our second formula. So now let's get into the meat of the question. You're finding your actual usable capacity. So how much can I get when I buy 1 TB? And your so you're using your M over S ratio now. And you multiply it by 1 TB. And you multiply by 1 TB. Then you is it subtract your FAT because M over S right now. Right. So your FAT size is 22 gigabytes. So how you would define your m over s. Now let's talk about how you define your m over s. So now that's the only thing missing. Then we can find how much by how much the manufacturers are scamming us. You understand? So the m over s ratio is defined as 10, sorry, 10x all over 2y. What this means is that your manufacturer will always represent it as 10 raised to the power something, and then your actual storage, will be represented as 2 raised to the power something. So now let's look at it. If the manufacturer tells you it is your the manufacturer tells you that your it is a 1 TB disk, 1 TB is 10 raised to the like tera. Yeah. Your tera is always your tera, the prefix tera, right? You can Google it if you're not really sure. But the prefix tera is 10 raised to the power 12. And then when you come to underground, it is 2 raised to the power 40. So in your microprocessors class, I'm sure you've heard that kilo is 2 raised to the power 10, and mega is 2 raised to the power 20, giga is 2 raised to the power 30, and then tera is 2 raised to the power 40. So we're using this for our calculation. And so your m over s ratio is defined as 10 raised to the power 12 all over 2 raised to the power 40 times 1 TB minus your FAT size, which is 22 gigabytes. So now the calculator gods, please let's go ahead and calculate it. Right. 10 raised to the power 12 divided by 2 raised to the power 40 times 1 terabyte gives you 909 gigabytes. I think. So let me quickly confirm. It gives you 0.09 terabytes, which by right now you know that the giga is 10 raised to the power 3 times, so you can present it as this, right? Then as I said, your FAT size, right? Your FAT size comes to add on to this one to give you 22. So it's, as I said, it's not fixed. It's not fixed. It differs. Windows has its own way of doing things, and our Mac has I think the NFTS way of doing things, the new file transfer system. Don't quote me on that, but that's what I think. Right? It's something that I've read some time ago. So then the old MS2 has the MS-DOS the file allocation table size. You understand? So adding your 22 to this gives you 931 gigabytes. And that's what gives you your total. Okay, I was just told by my advisor that it was I added something to it. It's supposed to be plus. Please let's make it plus. It's supposed to be plus. Please let's make it plus. It's supposed to be plus. So 909 plus 22 file allocation table size to give you 931 gigabytes. It seems what I was looking on wasn't the correct one. You understand? So this gives you actual usable. So as I keep referring to, this is what you get. So this is what you get. So sorry for the confusion earlier, but I hope right now you understand that that's the second formula that we'll be using. Understand? So you saw the question, right? If you've never heard of this before, this question will be impossible to solve. Like you can sit there for 2 years and then like you can't do it. Like if you've not heard of it, you really can't do it. So I hope like this will give you a way to think about it. So CO, what is the size of the file allocation table used by Martha 200? So in this case, you're finding your FAT size. So right now, like if I give it to you, I'm sure you can think about it, do some one-to-one. If the live stream ends right now, I'm sure you'll be able to find a way to solve it. You understand? Yes, and you can tell that M is known as 10 raised to the power something. Manufacturer always represent as 10, and then your actual sizes will be 2 raised to the power something. You understand? So it's giving you a good way to think about. I think that's all that I wanted to cover. Yeah, I think that's all I wanted to cover in the first part. So now let's begin then solving the natural questions because I'm sure that's what most of you came for. So question one. This is from the 2019. If you don't have the questions, right, open the, what do you call it, the stream. If you look at the description of the stream, you would see that I put a first folder and a second folder. Please check any of them. The names will be the scan one of 2019. Right? I'm sure you'll be able to. So what in modern computer technology, what's the difference between a microprocessor and a CPU? This question has hunted many people. So let's bring a distinction right now, right? The CPU is a component in the computing system, right? That is responsible for executing instructions. And the MUP, the microprocessor, is usually a single chip that implements or includes as a part of it the CPU. So a CPU is a component. So anything in your computer, in server, in anything, right, that executes instructions and interfaces with some IO device, right, is your microprocessor, is your CPU. And a microprocessor is usually a single chip, right, that implements a part of the CPU. So you see, the thing is that currently, right, even though they're outdated, currently there's some people who want to challenge themselves and have taken up electromechanical CPUs. They're building electromechanical CPUs or mechanical CPUs that are not electronic. Right? Microprocessor is strictly electronic. So that's the difference. So CPU is a bigger set because CPU when you look at under the CPU, you have something like a microprocessor. You also have something like a mechanical CPU. You have something like an electromechanical CPU. Those things, right? And somebody who can define a CPU as an abacus. It's not right or anything, but it gives you a way to think about it. Right. So I'm coming again with the two definitions. A CPU is the component of a computing system that is responsible for executing instructions and interfacing with some IO devices. And the microprocessor is usually a single chip, right? So in mind, it's usually a single chip because the CPU can also be thought of as multiple microprocessors, right? Different microprocessors that are interfacing together to give you a single CPU. So the microprocessor is usually a single chip, right, that implements or includes as part of it, right, a CPU. You understand? Very, very simple explanation. Very, very simple. If somebody you don't get it, type it in the chat and let me go over it again. Maybe with a different analogy. You understand? But that's the analogy that we're using today. Perfect. How do the address and data bus widths affect the performance of a microprocessor? If you're here from the beginning, you remember I said that the questions are very, very choice intensive. It depends on how you will choose to define it. So this question has no correct or right answer, right? It depends on how you talk about it. So now let me talk about it and then you can choose whatever you want. The address password. Right? The address password. So from my computer, as if you've ever been to the class before, you'll be able to you will know that the address will talk about the lines that are you transfer the address from. Right. So if I want to address, let's say, location 96 billion in memory, I'll transfer location 96 billion on that address bus. If I want to transfer, let's say, address 96 billion, there's the name of Otamaklu's father, right? That means that that particular name will transfer will come down the data bus with. You understand? It's something that it's a way that you look at it. Perfect. So now, how do they affect the performance of a microprocessor? You see, if you have a large program, then now let's look at it using this one. You have a large program, let's say that your program is 4 gigabytes in size. You're running maybe Call of Duty or something very, very wasteful, very, very like a program that requires a lot of memory. What will happen is that you need to access a lot of things at once, right? So your data bus will be running back and forth. So if your data bus is small, let's say 2-line data bus, right? The maximum amount of memory you'll be able to access is 2 raised to the power 2 times. Oh, sorry, I said address. I said data bus, but address bus. Right? If you have your address bus is just 2 lines, your AD bus is just 2 lines. The maximum amount of memory you can access is 2 raised to the power 2 times your width. So let's say that your width is equal for every situation. So you have 4 width. But if you have 16 address lines, right, 2 raised to the power 16 to give you times your width, give you 65536 times your width. You understand? So this one you can obviously look at it and see that if your program is large, right, your performance would by increasing your number of lines, your performance would be greatly impacted, right? So instead of moving four let's say 4 bytes at once, you can move 64 kilobytes at once. See, like think of it, not like you can move it at once, so but that's the maximum you can address, right? So you can get so much. So you can move everything into your ROM and then just be addressing it so quickly instead of moving 4 widths from, let's say, your ROM, because that's what your ROM can do, and then going forward and then doing some other things. You understand? Increasing your lines would help with large program execution. But that's also the thing. If you increase the number of lines, your number of memory spaces to index becomes exponentially larger. Look at it, C2 and then C65,536. It's the difference is very, very wide. So if your program is small or your program is a normal program, you understand, your processor it's heavily impacted because you're addressing something, and the smaller you address, the smaller space that the smaller number of lines, the smaller the amount of space that you have to address. You understand? So you will not need a lot of things, right, to address for, let's say, you want to address 4 kilobytes as compared to 64 kilobytes. You see the difference, right? So if you by increasing your address lines by just one, you double the amount of memory you can address. So that's where it is. So you can pick any of them. Many of them are valid answers, right? Based on the situation that is happening. If your program is large, you would benefit by having a larger bus, right? But if your program is smaller, it becomes wasteful and it impacts the performance of a processor. Right, now let's look at your data bus. So personally, I think, let me include my choice here. I would pick the about your large programs, right? Because nobody runs a small program these days. Right? So if you're looking for one to pick, you're really on the fence. Please go with mine, right? That by increasing the number of lines by just one, you can double the amount of memory you can access or you can address, right? And that's a huge benefit when you're running something that is really, really intensive. Right? My Call of Duty people would understand. Mm. Then you talk about your data bus, right? If you have a 32 bit microprocessor, but you can only your data is so small, like let's say 8 bit data, 32 bit microprocessor. By it's 8 bit that your data is in. To perform a 32-bit, let's say, addition, to perform a 32-bit addition, you would need a number of cycles. So let's look at it. If I want to add 1111, so we assume it's hexadecimal. I want to add this to 111 each, and my data size can only take 11. What I'll have to do is to segment it. So there's something called memory segmentation, where you separate up your operands. So I separate up 11, then I go and do my addition and then store it somewhere. I do this addition, store it somewhere, store it somewhere, store it somewhere. So that's what will happen. Right? You divide it. So you need 4 cycles to do a 32-bit addition. Very, very wasteful. Right? Very, very wasteful. So if your entire system does 32-bit operations, then for every single operation you need to do, you need like 4 cycles, and that's not good, because while I can just do 32 bits plus 32 bits, you're doing 8 bits plus 8 bits plus 8 bits plus 8 bits. Doesn't make sense, you understand? So that's the first one. Second one is that if you have a 32-bit microprocessor and then you are doing 30, you have 32-bit data bus, right? It can go very, very fast. You can do your operation, so you reduce the number of cycles, and you want to reduce the number of cycles that your data has to do for a single operation, and that's very, very good to understand. So that also gives you a cost trade-off. You understand? So if you want that will be my answer. Then my answer will be that you reduce the number of cycles that you take for your data to go through for each operation, and that will help improve the performance of the processor. It can also be that memory. So that's the second like choice that you can pick. That second choice that you can pick. That second choice you can pick. That since your data bus, let's say your data bus is Y lines. Okay, so your data bus is Y lines, and then your memory too, let's say that, because your memory is an actual memory, so there's something that is known as the bottleneck. This is an English word, I don't know why I said like that, right? Your bottleneck. Memory can become a bottleneck for you because everything is going according to the matching of your clock, right? Everything is going according to matching of your clock, but your memory is not really that fast. Your memory is not really that fast, so you can get this number of lines. You can go to memory and ask for this number of lines, and the memory will take some time before it gets to you. So increasing the number of your data lines, right, would introduce like a bottleneck into your system. I don't know whether you get it. If you get it, please let me know by typing it in the chat. So that's also the second one, that increasing the number of lines leads to bottleneck, and that affects the performance of your processor. So you can pick any of them. It's just the way that you explain it. You understand? That's why they said explain, not just it. It's an explanation that you are doing. The explanation that you are doing. So depending on whatever one that you want. So maybe you're running high programs. So for you increasing the address bus will help, and for you also what was it? For you also reducing the your weight of your data bus will also help you. You understand? It depends on the way that you explain it. So please pick one and then be on it. Now a solving question quality. Perfect. So two special microprocessor systems having n bit and m bit data. So let's go. Microprocessor A, microprocessor B. So let's say microprocessor A is n bit, microprocessor B is m bit. Right. And are related by the formula m is equal to n squared minus 6n quadratic. And given that the second microprocessor system has a 32-bit address bus, so important. So the second one has a 32-bit AD bus, and it can access a total memory of 8 gigabytes. So right now, that formula we went to, it will be coming into play. I think this is the only formula you need for the entire question, right? So first of all, what is the data bus length of the first system? We want to find data bus length of the first system. I've been given a formula that links it to be m is equal to n squared minus 6n. Right? This links your data buses together. So if you can find the data bus of m, you can use to find the data bus of n. Now let's look at it. You've been given some total memory. So S is 8 gigabytes. So 8 times 2 raised to the power 30 bytes. So you can represent this like S is equal to 2 raised to the power 20, 32, 33, 33 rather, 33 times 1 byte. You can represent it as this. Right? Because this is exactly what is happening. If you find 2 raised to the power 33, it will give you 8 gigabytes. And then since there's 1 byte, so we assume that we don't the assumption hasn't yet come yet. Like this is the wrong assumption, but I just want you to manipulate around with it, right? You have 2 raised to the power 33 times 1 byte to give you 8 gigabytes. This is a way of it. Or so as I said, like it's the wrong assumption because you have to figure out because what did they inform you? They told you that they told you that the second microprocessor system had a 32-bit address bus and can access the total memory. So if you have a 32-bit address bus, it doesn't make sense for 2 raised to the power 33 to exist. You understand? Because if your A is equal to 2 raised to the power 33, the number of address lines will give you 33. But this conflicts directly with what they told you that your address bus is 32-bit. You understand? So I hope you notice the difference. So that's why I said it's a wrong assumption. Okay, so now let's go on. So you've been given 8 times 230 bytes. So S is equal to A times W. But then A has been given to you in the form of, it's a 32-bit microprocessor. So 2 raised to the power 32 times some width will give you 2 raised to the power 33. So you do your calculations and then you realize that it is so it stores 2 bytes at each location. So it's a word addressable memory, right? A word addressable memory, meaning that there's 2 bytes stored at each place, or there's a word stored at each location. Yeah, so yes. Yeah, so you're looking for the length of your data bus. And then given that your data bus is the data bus width is 2 bytes. So what this means, right? What this means is that you have some number of lines. This is n lines. This is n lines. And that n lines can allow 2 bytes of data to travel on it. If you look at this carefully, you realize that it's just 16 lines. 16 lines are the only lines, are the only number of lines that can allow 2 bytes to travel on them. You understand? So W becomes your M becomes 16. What? Yeah, M is your number of lines, right? M is your number of lines. So M bit data bus. So you understand? So your data bus has a length of 16. Has a length of 16. Yeah, so we are looking for the first one now. So now you have this formula. where 16 is equal to n squared minus 6n. So the calculators. Yes, so you get n as 16, 16 and negative 2, I think. Is it negative 2? 8 and negative 2. And if you've ever like then if you've ever been born, that gives you can't have negative 2 lines. You can't have negative 2 lines. So we take this out and then n becomes 8 lines, right? So this is just by looking at it. You will never get a situation where your question appears as two positive numbers. You understand? They will never appear as two positive. If they appear as two positive numbers, there's a confliction with the equation itself, not with your answer. So please hold on. If you go and then you get something like 8, 10, for the lecture to come and give you your free marks. You understand? So your n becomes your number of data lines. So you have you have 8 lines, right? So the data bus length of your first system is 8 lines. That's it, 8 lines. So if the address bus length of your first system is 16-bit, what's the maximum memory it can address in bytes? Now we look at it. So if your address bus is 16-bit, what's the maximum memory it can address? Coming back to this same S is equal to 8 times W formula, right? They want you to find S. S is the maximum memory you can address. They're giving some A as 2 raised to the power 16, I think. Yeah, 16 bits because your address line is 16 bits. We have this. And then know that from your data lines, you have 8, so you can address 1 byte. I hope this like makes sense to you. So this gives you 64 kilobytes. Perfect. And this is your the data bus. This is your maximum memory that you can address with your first processor. I hope you understand how this is going. So by using one formula, there's no other formula you use. Just a way of manipulating and thinking about it, right? And you'll be able to solve every other question. And so many people would have fear when they see so many parameters. Please do not be afraid. The questions are very, very easy. The two formulas I give you and some facts that we'll discover as we are going along will just make the entire microprocessor experience. Like you go and sit down when you're just smiling in your exam hall. And yes, please, Elisa is open for donations. Please check the description box if you can donate to Elisa. This same has we've helped you so much. So let's go on. So number 3, consider the following instruction executed by a CPU with a 1.2 gigahertz clock. So the frequency of your clock is 1.2 gigahertz. Perfect. So right now, calculate how long it takes you to process the entire instruction from fetch to execute. So I didn't mention this. I didn't mention this. So this is one of the formulas that we also need, right? Okay. That's one of the formulas you also need. Frequency is equal to 1 over time. Physics waves. Frequency of the clock will be equal to 1 over the period of the clock. To understand. So if I give you the frequency of 1.2 gigahertz, I can find the time that it takes for one cycle to complete. So that's the period. Time for one cycle to complete. And yes, it's somebody just reminded me, right? If you want to post a comment or you want to ask a question, right, you need to subscribe. So please do that for us as we are here. So 1 over 1.2 giga. That's the amount of time it will take for one cycle to complete. So giga is 10 raised to the power 9. So you have 1 over 10 raised to the power 9 times 1.2. So this is how much it will take for one cycle to complete. So all you need to do for this particular question is to find how many cycles are in the system. To find how many cycles are in the system, you say that normal ratio and proportion. I want to reduce things as simple as possible that you can remember. If one cycle takes this amount of time will be taken by one cycle, you understand? So take 1 over 1.2 times 10 raised to the power 9. One cycle takes 1 over 1.2 times 10 raised to the power 9. Then x cycles will take will take x over 1.2 times 10 raised to the power 9. I hope you understand this particular formula, right? So you just need to find the number of cycles that it will take for this instruction to complete, and then you'll be able to find the amount of time it takes for your instruction to complete. You just multiply x by 2. If 1 is equal to this one, then x, which will obviously be more. So if 2 is 2 will obviously be greater, and if less will divide. So 2 over 1 times this thing. You understand? So this is a formula that please you need to keep in mind, because the questions, they keep occurring, right? They're the same questions but with different values and different ways of thinking about them. So right now, what we need to do is to find this. Um, so I think that for this particular question, so many of you have done your microprocessor project, but for every question that you will get, it's not the way that you did your microprocessor project that you would interpret the instruction. You would have to go according to x86, right? So let me look for it. I think I have the slide somewhere around. Just downloaded it yesterday, so I think it will be in the second one. No, third one. So for those who are like who don't know where the slides are, please um check your Teams page or check out the Google Drive for electrical students. Right, you'll find it under microprocessor slides. So I think let me go through. So there's the written form of the link. You get to someone under microprocessors, under files, under microprocessor slides. You'll find everything there, slides 2022. You find everything there if you don't know where the slides are. So yes, look at it. There's it. So how this is just an example. This is not actually x86, but this will give us a way of helping think about it. What do you need? You need to add the contents of the accumulator to the contents of register AX. So accumulator here, you need to add the content of register AX. So register AX, it's supposed to be somewhere here. As I said, this is just a way of thinking about it, right? Somewhere around here. And you need to move this from here to temp register within one clock cycle. If you know anything about um latches, flip-flops, memory locations, you realize that for them to work, you need a clock signal. It's the increasing side of the clock signal, or decreasing, depending on how it's edge triggered, how it's triggered. Right? And then you need to store the result in memory location whose address is held in register BX. So for the first cycle, your data will move to temp R, and then you see ALU operations do not take a clock cycle. No matter how we would want to think about it that way, they don't take a clock cycle. When they reach here now and then it's enabled, it takes less than a clock cycle for it to get here. So it's negligible. We just ignore it. So in the same second cycle, so the first cycle you move it to AX, you move the value to AX, then it adds in the second cycle, and then you need to store it in the memory location whose address is held in register BX. So register BX the value of register BX will have to go to the address bus, and then the data will follow. So you need 3 clock cycles. I hope that made sense to you describing it. So I need to come again and right. So you need to move the content of register AX into temp R, where the mouse is at the moment, right? And then after that, you need to store the result in memory location whose address is held in BX. So the address is held in BX, right? You're not storing it in BX. So the address will have to come onto the internal bus and then go to the address bus, right, to find where the location is. And then your data will follow on the data bus. So you need 3 clock cycles for that entire operation. So let me check if there are any chats or if someone understands it or doesn't. Oh, so it seems there's no chat around. That's fine. So there are 3 cycles that you will need, right? So how long it will take to process the entire instruction. So now you need, let me come again. You need 3 cycles for that particular instruction, for the execution of that particular instruction. So you need 3 cycles for the execution of that particular instruction. But they told you that um, how long would it take to process the entire instruction from fetch to execute? Assuming the time it takes to decode, the instruction is negligible. Neglect the time it takes to set up the memory address and perform the right operation. Okay, so we'll take out the memory address. I didn't read this part. We'll take out the time. So it takes 2 clock cycles because they told you that the time it takes to set up the memory address is negligible. To understand. So we need 2 clock cycles for your execution and your storage. So right now it's left your fetching. So your fetching is how long it takes to process the entire instruction from the fetch to the execute. Your instruction itself will be kept somewhere. So normally, I don't know if this is has changed or I'm not remembering it correctly, but normally it takes 2 clock cycles, fetch your instruction to increment your program counter and everything. I think it is somewhere here. Yes. So it will take 2 clock cycles to do that. In your third clock cycle, your IR is moving things. So it will take 2 more clock cycles to fetch. It will take this as a hard rule. There's no like way to think about it. But if you follow these, you would understand this. It takes 2 clock cycles to fetch your instruction. So 2 plus 2 gives you 4. So for that particular question here, it will take you 4 cycles. So 4 cycles, so 4 over this thing. So it would take 4 over 1.2 times 10 raised to the power negative 9 will give you 3.33 nanoseconds. So it will take 3.33 nanoseconds to execute that entire instruction. But you see, remember, look at the amount of marks for this question. You need to explain why it is 4 cycles you choose. You understand? Everything is very, very dependent on the way that you explain. So please explain it very, very well. Don't just go and then solve it to get 3.3 without explaining it. Somebody might also say that, oh, for his or her register, for his or her microprocessor, right? To fetch will take 16 cycles. You understand? It depends on how you explain because the MIPS architecture has a different number of cycles it will take. It will require for a fetch cycle than it will take for something like an ARM architecture. You understand? So it depends. It all depends on you. So now we can move on to number 4. The processor has an 8K address space. I think I should have mentioned this, right? The writing of the parameters is very, very important when you realize you don't know anything about the question, which will be very, very hard if you follow this tutorial to the end. But if you realize, Charlie, there's nothing for you, you can't solve anything, just write down the parameters and then try to use the 3 existing formulas I've told you about to reason about it. It's just thinking that you want to think. You'll be fine. You'll be fine. The processor has an 8K address space and 1K by 8, 2K by 8, and 4K by 8 RAM chips are available. Most of the questions have this format, right? A, B times C. This is how memory is specified, right? You have some value multiplied by this one. Remember the same S is equal to AW formula. If I don't want to represent my formula as 64 kilobytes, I can split it up and say that, oh, I store 16 bits or 2 words or 1 word, sorry. That's the width of my processor, and my address is 2 raised to the power 30, 2 raised to the power 16. Yeah, 16 raised to the power 16. Oh, 15 rather, because you are storing 1 word in a place. So then instead of storing 64 kilobytes, you can store um what is it 32 kilo by 2 words. By 1 word, I keep writing 2 words by 1 word, or 32 kilo by 16. This is the way that you can also write 64 kilobytes. You understand? The question like that. Question like that later on. Hey, we've come back to the Retabyte question. Yeah, so then if you look at question 2 right now, microprocessor has a 32-bit address bus. However, it's used in the design of a system in which the n most significant lines are never used. The design system makes full use. So they want you to find this n, x, n, and y. You understand? So you need to find it. So that's why I said that you need to keep it in mind. Let's go back. Perfect. So a processor has an 8K address space, and this one chips are available. So you have three types of chips available. How many RAM chips we needed to implement the entire memory space if you're obligated to use exactly two of the 1K by 8 chips and at least one of them? So getting back to your probability classes where you are required to use something, right? So you need to use two of the 1K by 8. So what this means is that you have 1K addressable locations, 1K addressable locations. You are storing 8 bits in each location. So you are storing 1 byte in each location. So this can also be represented as 1 kilobyte memory. I hope you are clear. This can also represent 1 kilobyte memory. And then you have 2K by 8 and then 4K by 8 also available. You have 2K by 8 and 4K available. So what are they asking you to do? What are they asking you to do? You want to implement the entire memory space. So be careful of the wording of the questions, right? This particular question appears in a different year, but they tell you that you need to implement half the memory space. With that one, the way that you would calculate it will change. So be careful of the wording. Don't see the question and just because the first three lines are same, then are just moving. Please read the question. If they're the same, then you can move. How many RAM chips we needed to implement the entire memory space if you're obligated to use exactly two of the 1K chips? So as I said, they're asking you that 8 KB. You have an 8 KB space or 8 KB addressable. They're telling you that you're supposed to use two 1 KB plus times 8. So how many chips would you need? How many chips would you need if you're obligated to use two and at least one of each? You're obligated to use at least one of each. So let's say that we use 2K, then we use 4K, one of each. So this is what the question has given you. You need to use two of something and one of each. How would you get? So you have 2 KB plus 2 KB plus 4 KB. You get 8 KB. So you don't need to do anything at all. Like they've just given you the answer in the question. So these are the free bonus marks that Tayanki wants to bless us with some of them. Understand? So you need to use three chips. Then you define why. Because if you use two of one, then one of each, and you get the full addressable memory that you want to do. How many address lines does the processor have? Yeah, sorry, hey, it's passing over my. I don't know what's happening this morning. So you need four chips, right? You need four chips. If any of you saw that and then you're about to type, please don't type. We've corrected ourselves. You need four chips. Perfect. How many address lines does the processor have? Interesting question, right? The processor can address 8K. So your addressable space is 8K. So 8K is 2 raised to the power 3 by 2 raised to the power 10. So you have 2 raised to the power 13. And if you remember, this 13 is the number of lines, number of address lines, you understand, to give you addressable space. So if you realize the questions are all around the same topic. And so if you've not gone to class the entire semester, you hop on this live stream, you should be able to get 40 over 40. It's so simple. I hope you're getting why. The formula the formula that you're using, they're all the same. So you understand it, Charlie. You are gone cry. So you need 13 lines, you need 13 address lines to like you need 13 address lines to your processor. You see, it's a one mark each. It's supposed to be very, very simple. Now, the chips have to be used in descending order of size, right? In descending order fractions in classes, right? Implement the system using simple gates only. This is a very, very interesting question. Like very, very interesting. Because if I don't know whether you've started noticing where the problem is, right? But you can't address it normally. So normally, how you are given it is that you're giving the same chip and you're told to address it. How you would address it? Hmm. Hmm. How you would address a processor, right, is to know the number of lines that actually run data. Um, is to know how many lines will run data. So let's say that I have a 10-bit microprocessor. and then I have a space that needs the number of address lines is 21. And please listen to this very, very carefully. Like everything I say is based on how other questions are framed. You understand? So we need to understand this. You have a 21-bit memory, right? Even though you have a 21-bit memory, 11 of the lines will go to waste because only 10 of them can use to run data. If you understand that statement, like you've solved the question already, right? 10 lines to run actual data and 11 lines are just useless because they can't be used to run data. A similar question which I want to answer right now and then not answer again is question 3. Please look at question 3 right now. It's a 4-mark question, so please look at it. A computer user buys a 32-bit microprocessor machine with 3 gigabytes of RAM installed. So right now, because of how this question is framed, we are solving another question to help us understand this. That's what's happening right now. So quick recap. The computer user buys a 32-bit microprocessor, right? And then it has 3 gigabytes of RAM installed. So you ask yourself that, first of all, given 32 bits, and what's the maximum amount of memory you can like address? That's 2 raised to the power 32 times like your width. Which so I didn't see this. When you are not giving the width in the question, you just assume it's byte addressable. You just assume W is equal to 1 byte. That's one thing that you need to know. Unless you are told that your data is you are giving your data bus length, or you're giving how much, or your data bus or your width, right? You assume it is 1 byte. So you have 2 raised to the power 32 times 1 byte, which gives you so please hold on, and there are some things going on. So yes, we are back. Seems the way I was thinking about the question, this particular question wasn't right. So like, we are going according to how we are doing it, and then later on we'll come back. So let's go on. Given 32-bit NUP, the maximum amount of memory, if you assume is byte addressable, would be that'll give you 4 GB. Right? This will give you 4 gig times 1 byte, giving you 4 GB. So the maximum amount of memory you can work with is 4 GB. You understand? No, come back. I just want right. And then he wants to upgrade the CPU's PC's RAM 6 GB as 3 GB of RAM proves inadequate. What will happen is that it's not a good decision because your maximum is 6 GB. So instead of buying new 6 GB, you can just buy 4 GB and then do your replacement. Right? It's a waste of money because you can't even interface something 6 GB with your 3 GB memory, with your 4 GB maximum addressable. Hope you're understanding how that how that works. So we'll come back and then come and actually look at it if that's the way that we need to talk about it. So looking at this question, yeah. So the chips have to be used in descending order of size. So this, as I said, like this makes it complex. Makes it complex. Oh, so descending order of size means something like this. Have your 4K here, your 2K here, and your 1K and another 1K. You understand? Then you have some lines A0 to A what? A0 to A12. Understand? Because you're using 13 lines. So A0 to So how do you go around this? Because for 4K, what will happen is that if you translate 4K, if you find the number of addressable for 4K, it gives you 12. So you use A0 to A11 will be used to run data. For 2K, it is 11. So from A0 to A10 will be used to run data. For 1K, it is 10. So for A0 to A9, we used to run data. So if you want to decide between 4 chips, and this is how your lines are. How do you work around it? How do you work around it? Understand? So this is how would go out go by it. First of all, you have to decide between your 4K and then your 2K. Because for 4K, A0 to A11 runs data. So only A12 can be used to decide. Right. So this is why. So when A12 is 0, you can did they tell you whether it was okay, so they didn't tell you whether it's active or non-active. So that gives us choice, right? So when A12 is 0, we can implement the 4K one. And then when A12 is 1, we can go to 2. This one is the choice I'm using. You can go either way if you want to. So that means that 4K is equal to A12 bar, and then the 2K one equal to A12. You understand? Because you're assuming it's active high. It's active low, it goes the other way around. This becomes bad, this is left open. So we use 12K to A12 to decide between your 4K and then your 2K. Now for 2K, not only your A12 is open, but also A11 is open up for you to understand. What will happen is that you would assume this is just one. You assume this is just one huge 1K chip. Just an assumption, we'll come back to it. And then we'll decide between your 2K and then your 1K. We'll decode between your 2K and your 1K. So we have A10 and A11. Have an A10 and an A11. A11. Yeah, so this one A10 is still running data. Sorry, this one A10 is still running data. So use your 11 to decide between your 2K and your 1K. 0, 1 by so when it's 0, you can choose to select your 2K. When it's 1, you can choose to select your 1Ks. But this is multiple, like this. These are a representation of the two. And now when you finally get to the 1K to decide between them, you can use A10 0 and 1, then your Y. So A10 chooses, let's say this is AKA, 1KA, this is 1K. You select between your 1KA then your 1KB. So right now you can decide between, but then how are you going to actually build a circuit that represents these three values? To understand. Okay. So for the 812, a simple NOT gate will do. So I'm just showing you how the individual ones to be implemented before putting them together. This is not actual circuit. So for the 812, this one can go into your 4K chip select, and this one can go into your K chip select. To understand. Yeah, this is how it will be differentiated. Now, because your 2K requires two lines to be selected, this one just can't go to the 2K. You understand? It has to be ANDed with something else. You understand? So when A12 is 1 and when A11 is 0, that is when you can see that, oh yes, you want to actually select the 2K. It's that. Or you can think of it as an or. It depends on how you would think about it, right? Any of them will work. So you can say that, oh, depending on any of them, not depending on just one of them, right? But with this one, you want to select two keys. So you would require the person who is running your data. You will tell him that, oh no, like I just want to be sure. You don't want it to be either or, you want it to be end. So it has to be both this one and this to understand. So you can take your A11 line, right? And AND it. So this is your A11 line, this is your A12 line and AND it together to get a select. To AND it together to get a select for your 2K chip, your 2K chip select. Now for your 1K, what will happen is that you need an A11, right? So A11 not. A11 needs to be, oh no, no, no. So this needs to be a not rather. This needs to be not because of how we define this. So your A11 needs to be high. A11 needs to be high. And then you can be able to select between your two 1Ks. So when your A11 is high and when your A10 is low, so this is an AND gate, you select your 1K chip. But if it goes the other way around, you select your 1KB. You understand? So there's this is the entire calculation you need to do. So I felt there was a question and then did this. Okay. So we need to use four chips because they told us that we are obligated to use two of the 1K chips and one at least one of each. So you want to fulfill a space of 8K. That's your obligation. You need to fill up 8K because they are told you to implement the entire memory space. And if you add 1K plus 1K plus 2K plus 4K, you would get 8K, you understand? But if it's not 8K that you're implementing, for example, you're implementing 16K, you need more. So that one it will be dependent on you. You can make 2K, maybe 6 or whatever would ensure that at the end of the day, you have an 8K, you have your address space, you understand? Depends on you. I hope you understand why we're using four chips. Okay, cool. Now let's erase it and let's actually build a decoding circuit. Okay, so 4K, the chip select, have some data coming in, right? The data is 13, it's 13 lines, I believe. Yeah, 13 lines. A0 to A12. So now when your A0 to A12 comes in, you won't use everything. Your A12, so this one will take A0 to A11. Then A12, I want to draw the circuit. This is how your A12 will be. Your A12 comes with not gate and it goes to your chip select. Perfect. Now for this, so this is an AND gate. This is an AND gate. For this, A11 will be here. A11 will be here. So you need to not A11 to this and AND gate to select your this thing. Select your 2K chip. Select your 1K chip. So your A11 itself will be used as one of the inputs to these things, to these two ones. You understand? And your second input will come from your A10. So if you can find a better way to draw the circuit, right? There's a way of drawing the circuit with vertical lines. A11, something like this. Also allowed to do it. Also allowed to do it. Make it simpler. So, but this your A10 line. Your A10 line needs to be knotted, and then it goes to your first one. The actual A10 line comes to this one. So that's how your circuit would be. Right? So, for example, to address your 4K, your A12 would have to be 0, and then your actual address will come. For your 2K chip, to select your 2K chip, your A12 will have to be 1, and then your A11 will have to be 0. Select something else. Please select your 2K. Now to select your 1K A chip, no. Select your 1K chip, 1K A chip, no. Your this is A11. Your A12 should be 1. Your A11, so your A12 can be I don't care for you here. It's not really a problem. It can be a don't care for you. Then your A11 needs to be a 1 because this is a 1. Right? It needs to be a 1. And then your A10 should also be a 1 for your AK1. Then your actual address will come. And for the other one, it is 10, then your actual address will come. So I hope this helped in you in your address decoding. Is there any other question? So we can move on to simple questions from here on. What's okay? So how many hexadecimal digits make up a double word? For this one, oh please, it is two. Two hexadecimal digits make up a double word. This is coming from the fact that one hexadecimal digit can be represented by 4 binary digits. You understand? Can be presented by 4 binary digits, one hexadecimal word, one hexadecimal value. Right? So this is supposed to be like 1 byte. 1 byte can be represented by 4 values. And then for a word itself, then that's 8. That's double. You need 1 digit. Now you need to convert from 4096 megabytes to gigabytes. 4096 megabytes, gigabytes. And like, so to convert from values that are just one step beyond the other, we have KB, you have MB, you have GB, you have TB. If you want to convert from TB to GB or from GB to MB or any of them, as long as they are one step beyond the below the other, use a factor of 1024 or 10 to the power 10, 2 to the power 10. So please, one of my advisors said something, and I want to confirm. I hope I said that one hexadecimal digit takes 4. So obviously, when you want to implement 2, which is a word, the word is 2 bytes. If you want to implement 2, you need 2 hexadecimal digits. I hope I said 2. So yes, I said 2. So you use a factor of 1024 or 2 raised to the power 10 if you want to like change from one which is directly above the other. if you want to change from one, so if you want to change from kilobyte to megabyte, or from megabyte to gigabyte, or from gigabyte to terabyte, I want to go the other way from terabyte to gigabyte, or from gigabyte to megabyte, or megabyte to kilobyte. You would do it with a factor of 1024. Now, if you want to jump steps, you just multiply by the number of steps that you are jumping. Just multiply by the number of steps that you are jumping. So let's say you want to jump from kilobyte to gigabyte. It will not multiply you. It would change by a factor of 2 raised to the power 20. You want to change from kilobyte to terabyte, it will change from by a factor of 2 raised to the power 30. I hope that one makes sense. Now, we're giving some megabytes and you want to change it to gigabytes. Obviously, divide by 1024. So this thing divided by this one. So yeah, so if you want to change from a smaller value to a higher value, it's a division. If you want to change from a higher to smaller, you multiply. So this gives you 4096 megabytes, gives you 4 gigabytes. Hope that makes sense to you. Convert from 6 gigabytes to megabytes. So yes, now we want to convert from a higher to a lower one. As I said, we'll multiply. We want to convert from 6 gigabytes to megabyte, right? So you multiply this by 10 and 1024 to give you boy Tamaklu. Tamaklu answer. So 6144. I feel it's a wrong answer, but we can't help it. Our resident boy in the house. So, oh, sorry, please. The answer was correct. So you have 6144 megabytes. Perfect. So, so we've come back to this question. As keep saying, the questions are all the same. Like it's just the same questions, except the assembly language. And assembly language are very, very unique. So, explain whether the following statement is true or false. In modern computer technology, all CPUs are microprocessors. When I was answering this question, I mentioned that is false, right? In modern computer technology, there's a difference between them, right? And that all CPUs cannot be processors. But the other way is true. All microprocessors are CPUs, but not all CPUs are microprocessors. Because, like, I'm drawing an image. You can keep it for, you can use to think about it. You can use to think about it, right? So you have broad CPU. CPU is the superset. Then you have MUPs. MUPs are basically just digital CPUs. Now we have mechanical CPUs. Mechanical CPUs. We have electromechanical CPUs. And you can also have another type of CPUs. Like I don't know, maybe somebody would make a CPU out of water. That one too would be classified under CPUs. But basically, all microprocessors will be CPUs, but not all CPUs can be microprocessors. You understand? Because mechanical CPUs are also CPUs, but they are not MUPs. You understand? So that solves that particular question. So you have to explain it well, right? In modern computer technology, you have general types, those words, like think about it and then write some good English to take the marks away. Very, very simple. A computer user buys 32-bit microprocessor machine. So with this particular question, we've already talked about it, but Kelvin Tamaklu, yes, please. So we can move on. We can move on. I wanted to confirm if there was something that you wanted to add to it, but it seems not. So now the 50 marks question. Yeah, so yes, so for most people, Chris solved it in class. Yeah. So for this particular question, you solved it in class. Yeah, so I think I want to upload something so that you can look at it. Where is it? I don't know. Let's send it. No, no, no. So yes, I want to show the solution so that I can explain it before we move on. And our good friend. So please ignore everything from here on the next few minutes, next couple of seconds. Yes, so while we configure, get to the question. Um, we are back. We are back. Perfect. So yes, a young engineering student is in the process of designing a new embedded system whose size, oh sorry, whose size is similar to a regular ATM machine using the only available 13-bit address microprocessor, a university lab. So you can read it, you can pause it and then read it if you're not on the live stream. So let me explain it, right? Hey, Jesus Christ. Okay, so okay, sure. So the type of circuit you need is a decoder, or more specifically, an address decoding circuit. Right? That's the type of digital circuit you need. The table below shows the list of active low chips. So this is important. Active low chips. Chips are only sold in packages, and the table shows their prices. Using the information below, what would the cheapest but most efficient design of the circuit above? If the design will be mass produced, only a single instance of the design will be needed. Assume the most efficient circuit is the one with the least number of gates. So first of all, for the microprocessor, we have a 13-bit MUP, and the maximum addressable memory is equal to 2 raised to the power 13 by 1 byte. The MUP is assumed to be byte addressable. So the maximum addressable is 8 kilobytes. Now, for mass production, for the 4K memory chip, right? So let me increase it. For the 4K memory chip, it costs 34 Ghana to buy a packet of 2 chips. And we can interface it directly with the MUP without any other circuits. So 2 underlined. For the 2 kilobyte memory chips, it costs 30 cedis. We need an addressing decoding circuit. So the MUP lines are follows. You remember what I said about the lines? Some lines will run data and some lines would be empty. So we use the empty lines for decoding the circuit. We're using partial address decoding. So because the reason why you're using partial address decoding is you want the most efficient circuit. If you do full address decoding, you need more gates. Like that one is basic thinking, like thinking about it. So the truth table for our chip select, use it. So because it's active low, when it's 0, it is selected. So when CS1 is 0, it is selected, and when CS2 is A 11 bar, it is selected. That's why we do it like this. If it's active high, it will swap. So we can implement a partial addressing with a NOT gate. So this is the decoder in question, just a line with a NOT gate in it. So this is it. A12 will be useless, A11 will go to a 1 to 2 decoder, come out, use to chip select, and then your 11 lines will be used to run actual data. You understand? So for the above implementation of the 2K memory, it is 30 CDs plus. It's in actuality it's 50 pesos because they told you 1 CD for 2 chips and 1 CD for 2 NOT gates, and you're using just 1 NOT gate. So it is in fact 30.50, but 31 CDs for just looking at it. So to implement two of the above, we need 61 CDs. I hope you understand why. Because 30.5 times 2 will give you 61. Now for the 41K memory implementation, it costs 29 for a packet of 4 chips. So same thing we are doing, implement your decoder, and we need 6 gates for the decoder, and then for 6 gates, because one is 50 pesos, you need 3 CDs. Add it to get 32. So compare all the cheapest for mass production be 4 kilobytes, because as you multiply by 10 CDs, as you multiply by 10 chips, as you multiply by 100 chips, as you multiply by 1,000 chips, for the difference between them increases. 4K is the cheapest by far, and for mass production, 4K RAM is what you need. Now for a single instance, we care about the overall cost here. We just want to do one. So meaning that if you're left with, if you have some leftovers, you don't care about it, right? You still spend the money. So that's the 2K RAM will be used because it results in the cheapest overall cost of 31 CDs. I hope you understand why. Because for the 4K, you use 34 CDs. For the 2K, you use 31 CDs, and for the other one, for the 1K, you need 30, I think 32 CDs. Yeah, so you need 32 CDs. So for the single instance, you would use your 2 kilobytes RAM. I hope you please understand how you get your answer. Now move on to 2016. Explain how a traditional ALU should be optimized for modern processor. So this particular question, I would have to check back, right? But the answer that I have in my mind is, first of all, you have to add MMX registers. Right? MMX registers support special instructions, right, called the SIMD. MX instructions can operate in parallel on data values contained in MMX register. So current processors have this, right? Current ALUs have this, right? They have MMX processors that can operate parallel, can do parallel operations. And then also the FPU, the floating point unit. You need a unit for performing floating point calculations. That's another one that you also can have. So you should explain it. At the floating point, currently you use more floating point numbers than actual values because of the some of the videos you run, because of the 3D data you've been working with. The floating point values are better. You need more, like for more accuracy, you need floating point values. So if you want to implement the traditional, you want to like convert a traditional ALU to be used in a modern microprocessor, you need to add these two things: floating point unit and then MMX registers. You understand, to help with parallel data, like parallel data operations. Perfect. So we've come back to number two. We've come to number two. The certain alien technology, memory capacity is measured in retabytes. It is discovered that the marketed storage capacity of the disk drives is always less than the actual usable capacity when a drive is formatted for use in an operating system. So look at it all. It is discovered that the marketed storage of the disk drives is always less than the actual usable capacity. So let's go to a fresh page. Let's work this out. So marketed. You have marketed and usable. Actual usable, right? So your marketed would, they told you that your marketed is always less. So your market is always less than your actual usable, right? Perfect. Okay. So like when you come to the in real world, what this will mean is that if you have 1 kilobyte, if you buy a RAM, a hard disk that is, for example, one kilobyte, they tell you that 1 kilobyte. When you go home and you put it inside there, you get something like 1.6 kilobytes. That's what this means. So and your marketed is always less than your actual usable. To use the knowledge from our own technology, explain why this discrepancy in values could be occurring. So this particular question could be occurring because the marketed is working on a different scale rather than actual usable. Marketed is on, so that's how you explain it, that in real life down here on earth, in technology, down here on earth, your marketed would always be 10 raised to the power x, where x is something, right? So if it's gigabytes, then you're increasing it in terms of 2 or 3 or 4 or 5, whatever. And your actual usable would be represented in 2 raised to the power y, right? Where your y2 would be 10, 20, 30, 40. You understand? That's how you do it. So that's how you explain that your actual marketed and then your actual usable, your marketed and your actual usable are working on two different scales. You understand? Perfect. A flash drive marketed with a storage capacity of 18 petabytes has a capacity of approximately 19.9 petabytes after formatting for use in an OS. If the alien OS uses a file allocation table with a fixed size 1 RB, what is the actual unit of petabytes? Oh, I've cleaned it. Okay, so let's write the formula again. So let's write the formula again, right? So your ratio, your actual usable, let's AU, not astronomical unit to ratio. So your ratio, your actual usable is equal to your ratio multiplied by your marketed value, your marketed plus your RB. That's your RB, right? So perfect, right? So in your alien, so in your alien, oh yeah. Yes. I think I mixed it up. I mixed it up. I mixed it up. I'm now seeing the error, right? When the ratio, right? When the ratio favors the consumer more, that is if your marketed is less than your actual usable, this is supposed to become negative. Supposed to become negative. Like your value here becomes negative. But if your actual is less than your marketed, which is what happens in real life, it becomes positive. So I said something, I flipped it the other way around. I'm now just realizing it, right? My my advisors weren't able to spot that, so please find Kelvin Tamakle and then beat him for that. So your ratio times your marketed minus your FAT, your FAT size. Um, your actual usable is equal to your ratio times your marketed minus your FAT size. That is for this situation. So please take a screenshot if you want to, but or write this down somewhere. When your marketed is always less than your actual, use a negative. You see, we use the actual. So you use the negative from this side, right? So now let's clean it and let's move. So please, I feel like this question here because of how I did it. So I'll go through from the beginning when we are done, so that we can use to explain a few things. So now you find your actual usable. So what did they give you? So your ratio. So you can keep your ratio in mind as S over M. You can keep your ratio as S over M multiplied by your marketed. So what was it marketed as? It was marketed as 18. You're finding the actual unit of a petabyte. It was marketed as 18. The actual was 19.95. The actual usable becomes 19.95. Marketed becomes 18. And then you're supposed to find your FAT size. Okay, no. You're actually giving your. So what are you finding? You're finding the actual user. Okay. Actual unit of a petabyte. So your FAT size was 1 RB. So now you have your all your things in your equation. 19.95 is equal to S over M. Now this is the ratio that we use to it will be used to compare between your actual and marketed. So if you want to find your actual unit of petabytes, you want to find the ratio between actual and then your marketed. I hope you understand that. Multiply by 18 minus 1. Move over this becomes 20.95 all over 18 to give you S over M. Kelvin Tamaklo, please your answer. Okay. So you have 1.1638 1.16. It won't change anything. Right. So now this is your ratio. So when you're finding the actual unit of a petabyte, you're not finding you have to find it in relation to something. So this is it. Your ratio between your a ratio between your actual marketed, right? Your marketed and then your actual usable would be this. And this is what represents your actual unit of a retabyte. I hope you understand it. Right. So the actual unit of a retabyte is represented by this ratio S over M is equal to this. So what this means in your formula is that if you want to find actual usable, it will be equal to the actual unit of a retabyte times your marketed value. Understand? So how much should I account for the error? So this is like an error, right? How much should I account for it to give me my actual usable? I hope you understand. You understand? Okay, so we can go ahead with the other question. What will be the usable space for a drive whose marketed storage capacity? We cleaned it. Okay. For a drive whose marketed storage capacity is 20 retabytes. 20 retabytes, but we've cleaned it to. Come on, please, what was the answer? Actual usable is equal to S over M times marketed minus FAT size. And your S over M was what? 1.16389. Okay, 9. Perfect. Times your marketed. So what was your, they marketed it as 20 retabyte minus 1 retabyte to give us quick maths. Please, Tamaklu, what's the answer? Tamaklu. You know what you're doing. No keep If this live stream becomes longer, please know who to. Your Elisa Vice President. So the actual value would be 22.76. Yes, retabyte. So this is your actual usable that you would have. And advisor. Yes, so confirmed by Paapa Kwesi agree. Yes, so it's to it. So if you remember this question too, we just did this question. That question, same like little question. So please don't slack. The same amount of marks. When it comes to like the first thing is to smile at the paper and then pick your pen and don't just write. And thank God for my life, you understand? Yeah. Don't thank God for Elisa. Thank God for me. Please let's continue. So are the following statements true or false? Explain. A. Increasing the width of the address bus in microprocessor system will improve its performance. Already solved this question. So you just need to think about it. It may be true or false depending on how you would explain. See how the explain is deepened. It is because you need to explain. Understand? It can be true or false depending on how you explain it. Right? If you decrease your data bus to it's either true or false. So you need to talk about it. The C is the only one that has an absolute answer. Right? A microprocessor is not the same as a microcontroller. Right? I don't know whether whether you've done that first of all, right? So a microcontroller has some things which a microprocessor doesn't have, right? It has a ROM, it has a RAM, it has IO parts, it has timers, it has analog to DC converters, right? Those are some of the things that microcontrollers have. And microprocessors do not have any of those, right? It doesn't have any RAM, doesn't have any ROM, and it has no IO ports. You understand? That's the microprocessor. And when your processor becomes like when you are using a processor itself, the processor would have IO ports, it will have RAM interfaces, to have ROM interfaces, but a microprocessor does not. You understand? So it's a false statement. Now, microprocessor has a 32-bit address bus. It is, however, so if I need to check, let me check if anybody has any question because we've gone so long that I've not received any notification. Okay, so it seems nobody has any question. Let us move on. A microprocessor has a 32-bit address bus. It is, however, used in the design of a system in which n most significant lines are never used. So let's write that. Let's write that down. Right? N represents most significant. So N is the most significant lines that are never used. You understand? Perfect. The design system makes full use of a total of 4 MB of RAM. 4 MB of RAM. Implemented with a single RAM chip. The RAM chip. So this is implemented, right, with a single RAM chip. If you remember, if you're implementing with multiple chips, that means you need more lines to address it. You understand? So if you're implementing with a single RAM chip, that means that it is direct. There's no other gates, there's no other decoding circuits. You do it direct. The RAM chip has a specification of xn by y. So xn by y. I think I mentioned this earlier on, right? That you can represent memories as this instead of representing it as storage values, and contains this memory's locations. So it's too big a number. So let's reduce it. 2 raised to the power. Yeah. Okay, sure. So from Paapa Kwesi Quansah, um, this particular value, this memory location, right, I'm presented as 2 raised to the power 21, right? So 2097152 can be presented as 2 raised to the power 21. So perfect. So now the rest of the question: what are the values? So this is your amount, your number of memory locations. So you see, this thing that we've written here, you can represent it. We can represent. I'm using a pencil. You can represent it as A times W, where your W is your Y here, and your A is XN. So if they've given you a number of memory locations, so you can write A as 2 raised to the power 21. We got this 2 raised to the power 21 from this. So you can find log 2, let's say A, to give you this. So the rule of thumb is that when given number of memory locations, if you want to find the number of memory locations, right? If you want to find the number of memory locations and you've been given number of lines that you have, it is simply 2 raised to the power number of lines to give you number of memory locations. If they've given you memory locations and then you are finding number of lines, it is basically this 2 log 2a to give you the number of lines. Such a simple formula resulting from our original formula. So right now we are up to like 6 formulas. Okay, cool. So you have a to be equal to 2 raised to the power 21, right? So what will happen is that you need to transform this into a form of this. So 2 raised to the power 21, if you remember, 2 times 1, your indices. 2 2 raised to the power 1 times 2 raised to the power 20 and presented as 2 raised to the power 21. And this would give you 2 megabytes, right? 2 mega. You still don't know the width. It will be 2 mega. So right now x becomes 2, n becomes mega. Now y, right? Y. You've been given 4 megabytes of RAM, and then you've realized that you have 2 mega. So if s is equal to 4 megabytes and a is equal to 2 mega, what would this be? So s is equal to AW. So you have 4 megabytes divided by 2 mega to give you 2 bytes. Simple, simple. So y gives you 2 bytes or 16. See, you usually want to represent it as a bit, right? That's the convention. So it is usually best represented as a bit. So y is equal to 2 bytes or 16 bits. So now we can present this as 2 mega by 16 bits. Wow. So perfect. So I'm so sorry. I keep erasing. Yeah, I keep erasing it. even not thinking about the next question, right? So we had 2 mega by 16. So the thing is that you want to find the n most significant address lines that are not used. So if you look at this and you realize that you used you used 21 address lines. Use 21 address lines to find your entire to do your entire memory space. If you have 32, if you have 32 address lines, then you realize that 11 will never be used. So 11 most significant will never be used. So n small n becomes 11. What this means is that you have 32 lines. The maximum addressable for 32 line microprocessor is 2 raised to the power 32. Right? That's the maximum. But you are using 21 lines. So meaning that you're not working at the full capacity. If you're not working at the full capacity, some of the lines are always carrying nothing. Right? So you need to find a difference, and that gives you 11. So small n is equal to 11. So 11 most significant lines will never be used to run data. I hope this please it makes sense. Perfect. So please I need to come again, right? Of internal clue. Given that a microprocessor has an address space of 8 kilobytes and only 1 kilobyte chips are available. So you see, this is the same question that was given to us in um in where are you? Where are you? In this place, and we are back. Hey, you've been on stream for almost 2 hours. Wow, shocked. Okay. So we'll be ending soon. Yeah, would have to divide the sessions, right? Yeah, sure. So you've been given an address space of 8 kilobytes and only 1 KB chips are available. So by like looking at it, you can tell that you need eight 1 kilobyte chips. Like you need to do something that involves 8 KB. And been given 1K chips. So obviously you need 8 1K chips. I hope this one they has like you have no choice. Hmm? Okay, yes. That's to implement full, like you want to implement the entire 8K. If you remember, before we began, I said that you may be needed to implement maybe quarter of the memory space or half of the memory space. So this one is it's a question of that, right? You want to implement half the memory space. So you desire to implement 4 KB. That's your desire. Your desire is to implement 4 KB out of this 8 KB. If I want to implement this 4 KB, you need 4 1 KB chips. One K chips. I hope this makes sense to you. So how many RAM chips do we need? We need 4 to implement half the memory space. Give the address range in hexadecimal of each chip that will be used in this implementation. That brings me back to another formula, another useful formula. We have to like 6 formulas right now. Yes. So if you want to find the range, still using a pencil. If you want to find the range of chips of a chip, right? A range of a chip. What you would do is that this is the formula, right? The range is equal to your initial where you start from 2. This is 2. Your initial 2n minus 1. Right? So that's where it is. Plus your initial. Plus your initial. So this one, they've told you that they are implementing 4K. So this is how you think about it, right? This is how you think about it. So in your hard disks, right, let's say that you want to increase your hard disks. So let's say you're using system of 256 gigabytes. Then you add another 256 gigabytes to it. Both of them are 0 to 256 gigabytes. Nobody is disputing that fact. But when you place them after the other, there's something called a memory map, right? When you place them after the other, it stops being from 0 to 256. So your first chip will be from 0 to 256. And second chip will be from 257 to 512. I hope that's that like I hope 255 to 200 and 512. I hope this makes sense to you. So the first one will take space from 0 to 255. Second one will start from 256 to 512. You understand? It stops being like that. It stops being 0 to 256 to follow each other. So if you want to implement 4 KB, and you're using 1 KB, so 1 KB, 1 KB. So this is in order. Right? So first of all, this is what you do. Right? So chip one will take from 0 to 2n minus 1 time plus initial. So 2 raised to the power n is. So, yeah, oh, sorry. So I didn't include the 1 KB. For 1 KB, 1 KB has like a space of 2 to the power 10. So did they tell you to put it in any value? Oh yes, I knew it. They will tell you to put the value in something hexadecimal. So this is giving you give the address range of the address range in hexadecimal of each chip that will be used in this implementation, right? So 1 KB can be presented as 2 raised to the power 10. So 0 in whatever will still remain 0. So 0 each, right? 0 hexadecimal. Now this thing. So 2n. What is 2n? 2 raised to the power 10 minus 1 plus 0. You have to change this entire thing hexa. So you get 10, 2, 3, right? If you do this calculation, you get 10, 2, 3, and as you change it to hexa. So nobody is coming to solve it over here. We're using the function to give you 3ff function on your calculator. So it is from 0h to 3ff to understand. So I'll leave the last two for you to solve, but I want to do the second one because it's quite different. So with this one, it will start from your initial. So wherever you end from, it's not where you start from. When you end, you have to add 1 to it to understand. So you end at 3ff. If you add 1 to it, it gives you 400 hexa. So this one starts on 400 hexa 2. 400. So same thing, it is 10, 2, 3, but you add 400 hexa to it. You understand? So 400 hexa plus 1003 decimal to give you. So to give you 7ff hexa. You understand? So this is the range of the second one. That's I'm compromising on the third one, and then you solve the last one. So you add 1 to this one to get 800 hexa. Then if you add it, I hope you can see the trend. It's increasing by it will change. SCO or something. So yes, you get BFF. Hey, such an interesting combination. BFF. Okay. So you get BFF in hexa. So this is it. So the thing I mentioned about the thing I mentioned about the thing I mentioned about the memory map, right? So I feel like this is not needed, but if you want to include it, Charlie, please feel free. So you have a memory map, right? Memory map is basically a map of the arrangement of your memories. So it's very simple. So you have some 1K chip here, right? That is having a range of 0 to 3FF each. Then you have a second one that's directly following it, also 1K, that has 400 each, 2 and 7FF each. You understand? You have a third one that has 800 each, 2 BFF each. I have a last one. So if I doubt anybody will reply in the comments, but if you know it, please put it in the comments or the live chat or whatever you see. So you understand? So that's the addressing hexadecimal. How many address lines does a microprocessor have? How many address lines? So the address lines will not be half the memory. It will not be the address lines won't be based on it won't be based on half the memory space, based on the full memory space, your 8 kilobytes. To understand. So giving some I'm writing here because we use some values. So giving some 8 kilobytes, how many lines will be needed to implement 8 kilobytes? Right. So the same formulas we've been using S is equal to A times W, where A is your total memory space, so 8 is KB. And I already told you in a previous one that you have the number, if you need the number of lines, given your total, sorry, your 8k, what you do is to use the log. Right? So log 2, 8k, give you a number of lines. So 13, according to Kelvin Tamaklo. Oh, no, it's not wrong. So the address lines of the microprocessor has 13 lines. And implement the chip select decoder using active low RAM logic. There's more. So yes, so I'm looking at how it is. And you see, as I said, the questions are very, very similar. So I'm sure after this first stream, any other stream, it will be so social, like 10 minutes, 10 minutes. Maybe another stream more, right? So that you can. So this is the only question that I think it's unique. We've not done yet. I think. So the second one, too, we've done it, right? Then the question. So yes, so implement the chip select decoder using active low. So as I said, be careful of um, the questions, right? Don't assume that because you've seen the first two phrases is the same thing as I was solving. I'm solving on the live stream. Understand? Implement the chip select decoder using active. So this is very, very easy. This is a very, very easy question. Hey, hey, sorry. So yes, you have some chips available. Some 1K chips. You have four 1K chips available. 1K, 1K. And then you have a MUP with 13 lines. But 11 of those lines are running data. So you have two more. Not two more, yes. 11, 10 of those lines will be running data, 10 of those lines, because 1K can only handle 10 lines. So 10 of those lines will be handling data and 2 will be left. And you use your 2. If they force you to use partial address decoding, it will be different than if they're forcing you to use full address decoding. So let's go both ways. Tell you that implement using partial address decoding. So I'm sure you know that partial address decoding is when you only use the needed. You don't use everything. So this one you have 3 lines too, but to select between 4, I'm sure this one you can tell from digital systems, you need 2 lines, right? So you need A10 and A11. 00011011, and you used to select it in order, right? So keep in mind that it's active low. When it's active low, represented by the chip select bar, right? So Y for the first 1K will be equal to A10, A11. You understand? Y for the second chip, right? 1K2 will be A10, A11 bar. Then you're going along. So 1K for the third one will be A10 bar, A11. And for the last one, be both bar. You understand? So this is A10, A11, A12. So for the first chip select, you just want to carry them like that. So you AND them and then you take them here. For your second one, you want to AND you want to not the A11. So you take it here and then you take your 11 from here. Right. So this is how you do it. I hope you can see the space is not really enough to. Okay, let me make some space. Right. So this is how it is. So let's do it for the last one, right? Then we can jump this question. Okay, so you want the A11 to become knotted and then the A12, the A11 to be standing like that. So you take your A11 just like that, this one, and you take this one knotted and you feed it into the same AND gate, right? Get here. So I hope you understand it. You just implement this circuit. So for full address decoding, what will happen is that you will still need the A12. you need the A12, so it becomes, let's go. You need the A12, so it becomes A12, A11, A10. Why? But the number of selections that you are doing still hasn't changed. It has to be first, second, third, or fourth 1K chips, right? It has to be any of them. So with this one, it goes 000, 001, 1, sorry, 010, 011, something like this, right? So when you're implementing this, y would be, for the first one, y will be equal to A12, A11, A10. For the second one, it will be A12, A11, A10 bar. For the third one, it will be A12, A11 bar, A10. And for the last one, it will be A12, A11 bar, A10 bar. So you do realize this will require more gates to understand. So if I have 3 lines, and I want to find if I want to select the first chip, I have to take all these 3 lines. And you do realize that there are no AND gates with 3 inputs, right? There are only 2 input NAND gates available. You have to do this. No, no, no. Like they're not physically you can't have 3 input NAND gates. You can only have 2 input NAND gates. Whenever you see something like this, what is happening behind the scenes is 2 of them are entering a NAND gate, and the result is entering another NAND gate. You understand? This is what gives you this. So in actual fact, you need 1, 2, 3, 4, 5 just to implement your first line. You understand? That's one of the things. Using active low RAM logic. That's it. So number 4, last question for this stream. Given that each microcycle requires 2 clock cycles, how long does it take a CPU with 1 GHz clock to execute 7 microcycles? So this question, we've gone through it before. Gone through it before in a different form. So if you already know how to do it, please pause the stream and then solve it yourself. Explore the explorer things we're doing over here. Okay, so let's go on. Finally, at each microcycle requires 2 clock cycles. So let's put it down. Each microcycle requires 2 clock cycles. And then you want to execute 7 microcycles. Just like I said, you don't want any complicated formula, ratio and proportion that they taught you in school. If 1 is equal to 2 clock cycles, 7 will be more. If more or less, we divide 7 over 1 times 2, 14 clock cycles. To understand effect. Now they've told you that they're giving the frequency of the clock to be 1 gigahertz, right? So frequency is equal to 1 gigahertz. So the time or period it will take to execute 1 clock cycle will be 1 over 1 giga. That is 1 nanosecond. Just because like giga is the inverse of nano. So you need 1 nanosecond for each clock cycle. And then just do your quick multiplication or you do your ratio and proportion. If one cycle was implemented in 1 nanosecond time, then 14 cycles will be more. If more or less, we divide 14 over 1 times 1 nanosecond, giving you 14 nanoseconds. Perfect. That gives you that's how long it will take the CPU to do that. So thank you so much for being on this live stream. We'll do the other ones later. I didn't realize the time had gone so much, right? So we thank you so much for being on this live stream. If you have any more questions, Silky of Intamaklu, at the Elisa office, the vice president, or you can ask for his number. His number will put in the chat for you to text him, right? So that you what do you- so that you'll be able to ask all the questions you want. If some of the concepts are confusing, please get it to us. You can send me a mail, right? The email is in the link description so that you can send a mail and we'll clarify it during the next stream. You understand? Thank you so much for joining us on this live stream, and I hope you'll get all the best in your exams. You understand? Have a lovely rest of your day. Bye bye.